Hey guys, Mr. Betts here. In this unit, we've been talking about how we're going to use calculus to solve real world problems. And one of the most common uses that we're going to use calculus for is something called related rates problems. And the idea of related rates is we're going to have quantities that depend on each other, where one of them changes and it causes the other one to change, but it's not a direct proportion how fast they're changing. So for example, I'm going to use an example here with a spherical balloon. And the idea is we're going to look at what happens when we put air into the balloon and how that affects the size of the balloon. And those two things, I guess I should say the size measured by the radius of the balloon. So putting air into the balloon is going to cause the radius to increase, and we're going to talk about how those are related to each other. So hence the name related rates. I do want to point out that the spherical balloon is kind of an oversimplification. That's something we tend to do in math to apply some sort of mathematical framework to a problem. So if this is a more traditionally shaped balloon, then the problem is going to get a little bit more complicated, but we could still apply the same ideas. This is a pretty common thing to do in math and physics. A lot of kind of funny physics jokes, if you're a physics kind of person, about like spherical chickens and spherical cows might be worth looking into if you're a little bored someday. But the question here is, what happens when we pump air into it? So from the most basic perspective, when we're putting air into a balloon, we're affecting the volume of the balloon. So as we add air, we're adding volume to the balloon. That's causing the balloon to get bigger. And so we want to be able to measure that change. So we're going to add a mathematical framework to it. And even though the balloon is probably not a perfect sphere, we're going to make the assumption that it is a perfect sphere. And as long as it's pretty close, this is going to be a pretty good representation of what's going on. So if we take this balloon, let's just look at it from a non-calculus perspective, a pre-calculus perspective, and talk about what happens if we just add 10 cubic centimeters of air to it. So again, when we add air, it's making the balloon get bigger because it's increasing the volume contained within that balloon. So if we add 10 cubic centimeters of air to it, obviously it's going to make the balloon get bigger. So we're adding volume, and by adding volume, it's also going to add to the radius. Getting back to what I was talking about at the very beginning of the video, these two changes are not going to be proportional to each other because the volume depends on the radius, but it depends on the radius with some formula that they're not going to be directly proportional. So we're going to be able to use calculus to make some computations here. Again, let's look at it from a non-calculus perspective first and just look at a series of adding 10 cubic centimeters to the volume. And you can see as we add volume, we add size, size specifically measured by the radius of the balloon. I do want to point out, though, if we look at the change in the radius, it depends, the change in the radius depends on how big the balloon was to begin with. So at first, an addition of 10 cubic centimeters makes a bigger difference than as the balloon gets bigger, the change is getting smaller each time. And the reason this happens is by adding volume to the balloon, essentially that volume that we add increases the outer part of the balloon. So it's almost like adding a shell to the outer part of the balloon. And as the balloon gets bigger, that shell that we have to add is going to get bigger and have less of an impact then. So we'll look more later at the exact relationship, but it's a pretty basic idea that as we add volume, we're going to add to the radius, and as the volume gets bigger, the change to the radius is going to be decreasing. So the calculus version of this question is what happens when we add just a little bit of air to it. So if we have a very small change in the volume, how is that going to affect the radius? So obviously the change in the volume is going to affect the radius, but as we might expect, it's still going to depend on how big the balloon was to begin with. So a very small change when the balloon is small is going to have a bigger impact than a very small change in volume when the balloon is big. So we're going to use this formula right here. Should be something you're at least a little bit familiar with. That gives us the volume of a sphere. And by looking at that formula, we can incorporate some rates of change, so some derivatives that would be related to this problem. Remember, dV by itself is just a really, really small change in the volume, and dr by itself is going to be a really, really small change in the radius. However, if we change those to dV dt, so the rate that the volume is changing with respect to time, now the change in the radius is going to be given by dr dt. So in these related rate problems, we're going to have derivatives that represent how fast some quantity is changing in the problem. And if I want to incorporate these derivatives in a problem like this, I can start with this formula right here and take a derivative with respect to time. So if we do that here, taking the derivative with respect to time, okay, so informally, that's kind of what I'm thinking in my head. On the left side, the derivative of v with respect to time is just going to be dv dt. So if you're thinking about how we would do this with implicit differentiation, the derivative of v would be 1, but since it's not a t, we have to multiply by dv dt. On the right side, we're again going to be using implicit differentiation. So this r here is going to be my inner function. Remember, pi is a constant, the 4/3 is a constant, so those are just going to tag along. So using the power rule, we're going to get 4 pi r squared. But again, I took the derivative there with respect to r, so I need to multiply by dr dt. I want to point out here something that's kind of interesting. I mentioned that a change in the volume is essentially going to add to the outer layer of the sphere itself, and the size of the outer layer is measured with surface area, and that 4 pi r squared is actually the surface area of the sphere. So the change in volume is actually going to be proportional to the surface area of the sphere, because when we add volume to it, then it's adding to the surface area. It's basically like adding a shell to the outer part of the sphere. So this equation right here gives us a relationship between how fast the radius is changing and how fast the volume is changing. So you'll see in one of the example videos that if we know how fast the volume is changing, let's say we have an air pump that we know how fast it pumps air into the balloon, then we can use that to figure out how fast the radius is changing for various sizes of the balloon. So we'll get into that problem a little bit more specifically in the example video. So the keys here in related rates problems is we need to be able to see in a problem a rate and understand that that's going to be treated as a derivative. So anytime something is changing in a problem, that's going to be treated as a derivative. And then we can take relationships that we know, either given to us in the problem, or maybe from a geometry relationship that we know the volume and the radius of a sphere are related to each other with that formula, and do calculus with that. So some big indicators that we're going to see rates would be, first of all, units. If we see units that are some sort of unit per some sort of other unit, that's a big hint that that's going to be some sort of rate. So we have miles per gallon, gallons per minute, meters per second, dollars per unit. These are all rates. I do want to point out that not all rates are obvious like that. They don't all have that per. So the way electrical usage is measured, the rate that electricity is used is in kilowatts. That's not obvious that it's going to be a rate. So there's going to be some other context clues within a problem that might indicate rates for things like that. That's not a real common one, though. Also, this may seem kind of obvious, but if we're told that something is increasing or decreasing, or some synonym like it's rising, so it's going up in the air, things like that are indicating that something is changing. So that's going to indicate some sort of derivative. So some sample related rates problems. These are things that we might see and use related rates on. So we saw the radius of a sphere related to the volume of the sphere. We might have the side of a square related to the area. So as the side of a square increases, the area is increasing, and those two are related to each other, and we can use related rates to solve that. We might have a point moving along some function, and that point is going to be a corner of a rectangle. So as the point moves along the function, the area of that rectangle is going to be affected, and those can be related to each other using calculus. We might have some company producing some manufacturing whatever thingamajigs, whatchamacallits. It could be actual real life things, and I probably have a typo here. Those are supposed to be the same thing. But we might know how fast the company can produce things. We might be able to have some sort of relationship that tells us what their profit is going to be for selling a certain number of things. And based on those two things, then we can say how fast their profit is changing, whether it's a rate by the day or by the month or whatever. We can use relationships to tie those together. We have another geometry one here where somebody's driving along a street. Somebody is offset from that street, so we want to know how fast the distance between two things is changing. So we might have Jill driving north on A Street. Usually A Streets are running east-west. That was a mistake. But let's say Jill's driving north, and we want to know how fast the distance between Jill and some other point is changing. Then we can create some sort of geometric relationship and use calculus to solve that. So lots of different types of problems that we can solve using calculus and related rates. And the key to getting started is recognizing the rates in the problem and recognizing the rates that might be asked for in the problem.